Every textbook defines a star by one rigid rule. It is a nuclear furnace. It is a sphere of hydrogen gas compressing its core until it ignites a blinding fire of nuclear fusion. Without that fire, a star simply cannot exist. But the James Webb Space Telescope recently peered into the cosmic dark ages, looking back 13.5 billion years to a time when the universe was supposed to be a featureless soup of gas. In that void, Webb captured the signal of JADE's GAS-GS Z14.0. It is a structured, hyperluminous giant shining with the brilliance of a billion suns, sitting exactly where our current models predict nothing this massive should exist. To build an object this bright, you need either more ordinary matter than was available in the early universe, or a much longer runway of time than the 290 million years our timeline permits. Gravity is too slow a force to have assembled this much mass so quickly. If this were a normal, young galaxy, its light would be a messy overlap of signals from billions of individual stars, each with different temperatures and chemical reactions. This is a chart showing the light spectrum Webb returned. Instead of chaotic noise, the data drops into a massive, sharp crater at exactly 1640 angstroms. That is the precise fingerprint of cold ionized helium. Theoretical models show that a galaxy cannot produce a signal this uniform. This spike belongs to a single concentrated source of light, one individual object that is physically too cold to be undergoing the hydrogen fusion we see in our own sun. This decouples the identity of a star from the requirement of nuclear fire. We are looking at a giant that burns, yet remains cold. These giants are likely fueled by WIMPs, weakly interacting massive particles. These are the particles theoretical physicists believe make up dark matter, and in the early universe, they were trapped inside this star's core. Because WIMPs are their own antiparticles, they self-annihilate when they collide in high-density environments. This process converts their mass directly into heat, providing a steady outward pressure that keeps the star stable without ever needing to fuse a single atom of hydrogen. For decades, we spent billions building underground detectors like Lux and Xenon, waiting in complete silence for a dark matter particle to strike a sensor. We were searching for a ghost particle that drifts through normal matter without ever touching it. Dark stars suggest we were simply looking in the wrong place. These giants prove that dark matter can and does collide physically, provided the environment is dense enough. In this era of the cosmos, dark matter becomes the primary fuel source for the first generation of stars. Normal fusion stars have a strict growth limit called the Eddington limit. If a star grows too heavy, the violent radiation from its nuclear core blows its own fuel supply away, stopping its growth. A dark star bypasses this limit entirely. Because its core is heated by dark matter annihilation rather than violent fusion, it produces no harsh radiation wind to push gas away. It can relentlessly devour surrounding hydrogen clouds for millions of years, growing heavier and more massive without resistance. This allows a single dark star to swell to a diameter of 10 billion kilometers. If you placed one at the center of our solar system, its outer atmosphere would stretch past the orbit of Saturn, swallowing every inner planet in a cold green fog. By bypassing the physical barriers of stellar evolution, these objects become millions of times more massive than our sun, leading directly to a unique and silent death. Eventually, the dark star exhausts the supply of dark matter at the center of its orbit. The annihilation engine slows down, and the outward heat pressure drops. When a fusion star dies, its core rebounds into a violent supernova. A dark star has no nuclear fire to resist the inward pull of its own immense weight. The entire 10 billion kilometer balloon of gas implodes in a fraction of time. It falls down its own gravity well, compressing millions of solar masses straight into a single point of infinite density. This collapse is clean and immediate, creating a supermassive black hole without a supernova explosion. This solves the mystery of how supermassive black holes existed so early in history. They didn't grow through billions of years of slow feeding. They were born massive as the corpses of these dark matter-fueled giants. Webb is now finding hundreds of little red dots, hyper-bright objects appearing throughout the early universe. Astronomers initially mistook them for entire galaxies containing billions of stars. Webb spectrometers reveal these are single sources of light where hydrogen gas is swirling at 3.2 million kilometers per hour. That is over 2 million miles per hour, a speed that defies normal orbital physics. These red dots are the physical evidence of unimaginable gravitational wells. We are watching the transition as massive dark stars collapse into the first supermassive voids of our universe. The data is replacing our model of a slow fusion-based ignition with a universe that began through the energy of dark matter annihilation. We are finding that the first light in the cosmos was fueled by the invisible.